geothermal energy resources. There's also near surface problems, like for example, geotechnical examples, looking for contaminants or things like unexploded ordnance. So this is a wide array of problems that all have in common that electrical conductivity can be a diagnostic physical property. And so EM geophysics perhaps has a role to play in each of these problems. And so just as a refresher, I'm sure most folks here are familiar with this, but electrical conductivity or resistivity, we're quantifying how easily current passes through a material. And this depends on a lot of factors, which is why it is a useful physical property. It depends on mineralogy, the porosity, permeability, the nature of the pore fluids, whether they're saline or rather fresh. And you can see that for different rock types and for different fluid types, we have resistivities that range over many orders of magnitude. So things like massive sulfides being very conductive, whereas if we talk about igneous and metamorphic rocks, those are going to be quite resistive. And so depending on the problem that you're looking at, conductivity can be a very diagnostic physical property. So if we talk about, a cartoon of what a geophysical survey is we've got some sort of source that's going to input energy into the subsurface and generate a response that depends on the physical properties of the subsurface. And if we're talking about electromagnetics, that's going to be conductivity or resistivity. It's inverse. That's this sigma symbol. It also depends on the magnetic permeability and the dielectric permittivity. But generally with EM experiments, conductivity is the big kid in the block and the main thing that we're sensitive to. And so as we talk about EM experiments, there's many different flavors. We can first talk about, categorizing them by the source. So we can think about grounded sources where we, stick electrodes in the ground and we inject a current, or inductive sources where we're perhaps using a loop. The nature of those sources can be controlled or natural. So controlled source being something that, we're in control of the waveform, whereas natural sources, we're using ambient EM energy. We can also categorize electromagnetic problems in the frequency domain or in the time domain, and that's based on the waveform that's used. So if we talk about a frequency domain experiment, that's going to be a harmonic waveform, whereas if we're talking about a time domain experiment, we're using a transient waveform. And we can position sources and receivers in a bunch of different places. We could choose to do, an airborne survey on the ground, in boreholes, or any combination of these. So there's quite a bit of flexibility with how we set up a survey, and that's going to depend on what it is we're looking for. And so let's start off with just sort of grounding ourselves in the physics. Let's think about, for example, an inductive source experiment where we're looking in the time domain. And what we're going to do is we're going to put a transmitter, a loop transmitter at the origin here at 0. And we're going to just use a step-off waveform and measure the dB dt, which is the time rate of change of the magnetic flux through that loop. And so, depending on if we have a half space, so if we have a half space on a log-log plot, we're going to see, a straight line here. But if we introduce a layer, we're going to see some, variation in that dB dt that depends on the conductivity of that layer. And so to understand kind of why this is the case, it can be useful to look at the fields and fluxes. And so what we're going to do in this next slide is I'm going to simulate a couple of examples. We're going to start off by considering basically the scenario that corresponds with the black line where we just have the background. So the conductivity of this layer is just going to be the same as the background. We're going to look at 10 to the negative 2 Siemens per meter throughout. And then we will look at the currents on the left, and we're going to look at dB dt on the right. So I'm going to play a little movie here. This dot shows us both where our source and our receiver are, and we're going to use a step-off waveform. And what you're going to see is that as soon as I hit play here, you see that immediately the time starts moving and we have currents that are induced in the earth, and they slowly decay and diffuse away. And you can see that the colors kind of disappear pretty quickly, but you can still sort of see the time rate of change of the magnetic flux, slowly, smoothly diffusing downwards and outwards. I'll play this once again and just orient you on a couple of things. So the red and the blue in the current density basically tells us we've got currents going, some of them are going into the page and some are coming out of the page because we've got an inductive source. So those are going to loop around. And then the dB dt is the curl of that. And so that's why we see these vector plots. And you sometimes hear the response referred to as a smoke ring, and you can actually kind of track the center of that ring with the center of the BDT here, which is kind of cool to see. So you see that, at early times, we're really sensitive to the near surface and right sort of near our transmitter and receiver, whereas at later times, we're going to be sensitive to a larger volume and to deeper. So that was just a half space. Let's go ahead and introduce a conductive layer. So I'm going to introduce a layer that is 1 Siemens per meter. So that's this conductive one that played right away. Oh, sorry, that was the same video we were just looking at. Let me flip the slide. Pause this and we'll flip the slide. So the one we're going to look at here is now going to be the 1 Siemens per meter layer. And so you see, early on our dBdt is actually lower than the half space, and later on it's higher. And so you can perhaps try and reason about that. But let's actually look at the physics and see if we can learn anything from the physics. And so again, we've got our current, we're going to turn it off, and what we'll see is we'll see that currents are induced in the earth right away, but then all of a sudden, very rapidly, we see the currents concentrating in this highly conductive layer, and they decay very slowly. And that's basically why you see early on this sort of lower signals, but later we see more signal because we're seeing that slow decay of the currents. And because we're looking at the time rate of change of the magnetic field, we need the currents to be changing in order for us to see a signal. And so this gives us a bit of a flavor of, one type of experiment, an inductive source time domain experiment we can, look at to see that we have sensitivity to subsurface conductivity. We can also look at frequency domain experiments. And so in this case, we talk about, a harmonic signal. And I find that the physics, more intuitive to think about in the time domain. But what you can basically do is kind of relate time domain and frequency domain and think about high frequencies being related to early times. And so here, for example, we're sensitive with a high frequency very much to the near surface. Whereas if we go lower frequencies correspond to somewhat later times. And so we're sampling, a larger volume of the earth. And that you can also quantify by looking at the skin depth, for example, which tells us effectively how deep we're seeing depending on the resistivity of the subsurface as well as the frequency. And so this sort of talks about the forward simulation, about the physics. And in general, what we're doing when we have geophysical data is we're interested in the inverse problem. And so we have some data, we perhaps have these dBdt measurements, and the goal in that case then is we want to find an Earth model that has given rise to those data. So given our data, some assessment of the uncertainties and the ability to forward model, that means basically solve Maxwell's equations in either 1D or 3D, and be able to predict data given a model of the Earth, we want to go ahead and try and take those data and find a model that's consistent with those data. And the way we typically formulate this is as a optimization problem, where what we're trying to do is to minimize data misfit terms. So this phi-d, basically a constraint that we want to fit the data, and then our model norm is going to impose geologic constraints or assumptions that we have about the model. And so then we pick a beta that tries to sort of balance these two so that we're fitting the data and our geologic assumptions. And so, there's a lot of research that our group does in this. And as what was mentioned, we develop open source software for forward simulations and inversions. And this is a project called SimPEG. And so the website link is here. And there's a lot of resources that you can access from that website. But basically our goal for this project is to have it be a common framework for simulations and inversions for a wide array of methods. And so although today I'm talking about electromagnetics, SimPEG also does gravity, magnetics, and then the static version of electromagnetics, DC resistivity, IP, and there's some things plugged in for fluid flow as well. And the goal really of having it be an open source project is to have it be a space where researchers can rapidly build upon the work of others. And I found that especially working in a research environment, working with students, for somebody to be able to pick up and start a new idea, having a modular framework where they can really rely on all the work that's been done in the past, but plug in their new piece, plug in a new regularization or perhaps a new forward simulation, makes it just a lot faster to be able to sort of get to the space where you're playing with new research ideas. And it's also been really important for helping facilitate connections with industry. The way it's licensed is it's the MIT license, which is a very permissive license. Folks are able to pick up, adapt, and use the code as long as it's attributed that it has come from SimPEG. But you can use it for academic purposes or for commercial purposes. And so this is what, when I showed you those movies, that's the forward simulation that we were using for that. So coming back to our title, we're looking at, EM geophysics from shallow to deep or across the scales. And so I want to actually look at some of the different scales. We can be looking at thinking about sort of near surface problems to depths of hundreds of kilometers. As I mentioned, we can be looking at inductive or grounded sources. So grounded sources, we're typically going to see a little bit deeper, although, you can use large loop inductive sources to see deeper. And natural sources are going to see deeper as well. And so we can also, categorize this by an array of, different types of systems. So if we've got grounded sources, we can be looking at, DC resistivity, or we tend to be looking moderately shallow, although the further you get those electrodes apart, we can start to look deeper. There's inductive source EM systems like the totem, where I used a lot for agricultural and groundwater applications, where an EM system is towed behind an ATV. Can tow things from the air, and that's going to help us start to see deeper. And as we go deeper and deeper, we want to actually be using natural sources where we can really take advantage of the very large plane wave sources. So we can relate this back, let's relate this back to some of the problems that we used as motivation initially. And so you can see here, we've got an array of problems where we're looking, from shallow to deep. And so let's look at some of the challenges that perhaps surface with each of these. And so I'll start off with examples from, for example, CO2 sequestration or hydrocarbons or wastewater injection. These are all, examples often in sedimentary settings where we have steel infrastructure, which is quite challenging from the numerical side of things in terms of being able to simulate EM experiments in these settings, because you have these very thin, very long structures that are highly conductive and magnetic. So steel is, for example, on the order of 5 × 10⁶ Siemens per meter, which is 6 to 7 orders of magnitude, often more conductive than the background. And it also is typically highly magnetic. And so what we've done to be able to simulate these types of problems is we've actually developed cylindrical meshes in SimPEG. So we can have a geometry that conforms to steel casing, so we can discretize that quite finely and be able to input these very high contrasts. And what you actually see that's kind of interesting is if we take this example here where we've got a background of 100 ohm meters, and we've got a 10 ohm meter, a more conductive target that we want to see in the subsurface. If that casing were not present and we're trying to see a kilometer deep, you're going to be very hard pressed to see that target. So here we're simulating the currents just in a DC resistivity experiment. You can see a little bit of deflection due to this target, but if we look at the data on the surface, if there's no casing, we're just measuring the radial electric field, there's no measurable difference between if we had that target and if we did not. But if we have a steel casing present, so we have this now highly conductive, essentially extended electrode, it helps us deliver current to depth. And so you can see here that this target, really lights up. And if we measure data on the surface, we can actually see now, in this case, if we pick a noise floor of 10 to the -7, we can really see a measurable difference between if we had the target and if we didn't at a kilometer depth. So although there's some challenges here with the scales, there's also some potential opportunities to take advantage of these highly conductive infrastructure. If we pick a different scale, we think about, minerals or geothermal. The challenges there is we often want to be seeing on large scales and seeing very deep, especially as you talk about seeing undercover or mineral systems. We want to be able to see quite deep. And so in that case, we're relying on natural sources, so solar wind and lightning strikes. That's going to generate this ambient electromagnetic energy. And so you can see an example here where we're looking at, for example, the spectrum of ambient EM energy. So lower frequencies help us see deeper, and higher frequencies are a bit shallower, so we can span a spectrum there. But the challenge, of course, then is we don't have control over the source, and so then need to work with transfer functions of the field or ratios of the field to get rid of the effect of the source. Now, if we go to a very different scale, if we talk about unexploded ordnance, we're looking at, now small scales and very near the surface, or perhaps there's, a lot of interest in marine settings as well, near the sea floor. And we're looking for fairly small targets. So this is an example of a UXO, and that's a pen for scale. So that's a fairly small target. And you might be looking at, areas of land that are acres, and you're looking for small targets like this. And in these settings, there's also, often clutter. So you can be looking for things that are perhaps UXO, but, there's things like pop cans or scrap metal around as well that also have an EM response. And so we need to try and be able to use EM data to be able to tell the difference between something that looks like a UXO and something that looks like clutter. So that's a bit of a sampling, and what I wanted to do next is go a little bit deeper into 3 different examples that I'll walk you through in mineral exploration, in water, and unexploded ordnance. And so we'll start with an example looking at groundwater. And so this is a project that we were involved in back in 2020, just before COVID, where we got connected with some folks in Myanmar and applied for a Geoscientists Without Borders project, working on improving water security in Mon State in Myanmar. So the map here is just showing you where that is. And so the general goals of the project were to bring geophysical equipment to Mon State, to train local stakeholders. So these are local engineers and geoscientists with the local geologic surveys there. And to then also provide, open source software and educational resources for these folks to be able to take the data that they've collected, be able to invert those, and also be able to, importantly, connect with the open source community if there's questions that come up, and have avenues for continued communication even after the North American team had left. And so there's a few important components to this project. One of the things we found extremely useful was to basically have this kind of 7-step framework that we used for all of the case studies, where we'll sort of walk through strategically how we define the problem, how we define the physical properties, and the data processing workflow. And I'll show you an example of how we're doing this. And this proved to be quite a valuable communication tool. And then also we developed, based on SimPEG, a lot of Jupyter Notebook apps, and these are all available. You can take a look at them through these the geosci.xyz website. And so with some of these, what we did is we've got examples where we've hooked up basically the SimPEG code to some widgets for specific examples where we can show fundamental aspects of the physics. So here we were looking at being able to simulate a 3-layer Earth, and being able to show what happens if you change the resistivity or the conductivity. What do you expect the currents to look like, the electric fields, and then the data. And so here we were showing, for example, the difference between a Wenner and a Schlumberger sounding, and how the different electrode spacing helps you see different depths in the Earth. And so let's walk through an example in one of the villages that we worked in, so Fair Nagotato village. So this was a case study where actually in 2018, they had run a DC line, but they did only 1D inversions. And that suggested that there was an aquifer at 30 to 50 meters depth. They drilled past 30 to 50 meters depth. They drilled down to 60 meters depth at the center of the line. So the survey line is here. So they drilled at the center and unfortunately did not find any significant water at that point. And so in 2020, what our team did is returned there and conducted this 2D survey along this same line. And so the goal is to try and see, okay, with 2D surveying and also 2D inversions, can we actually see where there is significant water? And so the next step in our 7 steps here, once we've defined the setup, we've defined the problem, the next stage is to identify the physical properties. And so based on some geologic logs in the area and sort of understanding of the different geologic units that are expected, we have a bit of a conceptual model here where we've got a range of different resistivity values. And kind of the key takeaway here is there's 2 potential areas where we could have a sand aquifer or we could have fractured deeper aquifers. And in general, this is kind of the target because these are less susceptible to seasonal variations. And so roughly what we're looking for is, the main water bearing regions are on the order of 40 to 140 ohm meters. And so the next step is okay, what's the survey we're going to run? And so went out and ran 2 different survey configurations, is a Wenner-Schlumberger and a dipole-dipole. And then we show an example here of, how those data are set up and plotted in a 2D pseudo section. And so went out, collected the data, and as we all know, there's a number of different ways you can visualize data. So looking at data in pseudo sections, but it also can be useful to look at histograms to be able to start to set up noise levels and try and assess high quality data versus noisy data. And so we take those data, and then the goal is to then through inversion go ahead and try and estimate a physical property model that is consistent with those data and can be interpreted geologically. And so we set up some notebooks where they could go ahead and actually, run an inversion, look at your Tikhonov curves, so look at the misfit and the model norm, and choose a model based on that. And so this is the model that was resulting. And if we take a look at this, so the center of the line basically is where they had drilled the 2018 hole. And we see, there's hints of perhaps something that is in the lower resistivity range here. So around the range that we were looking for. So blue is water in this case. But here we've got this very intriguing region where we see, resistivities on the order of 10 ohm meters. And so this is where we, suggested to drill. So the next question is the synthesis is, does our setup, did we actually answer our original question at hand? And so they did drill that hole in 2020. And we were successful. There was over 1,000 gallons per hour of potable water coming out of this aquifer region here. And so since then, the North American team left, but they're left equipment there and also, open source tools for them to be able to go ahead and continue, collecting data and processing data. And so there's been field surveys conducted at least 23 different villages by the engineers and geoscientists there. And there's been a couple of other successful drill holes spotted by the teams there at this stage. So that showed you an example where we're looking, relatively near surface and on the static end of Maxwell's equations with DC resistivity. And so the next example that I'd like to show you is in mineral exploration. And so what we're going to look at here is the Tleek-Waicho kimberlite complex in the Northwest Territories in Canada. And so this was a geophysical discovery in the 90s, entirely by airborne geophysical magnetic and EM data. And there were 2 kimberlite pipes identified. So there's this DO27, which is on the southern end under the lake here. And then DO18 is further north. And we kind of have this conceptual model of the kimberlite deposit where we've got a few different kimberlite units. So there's the HK unit. This is this hypabyssal. It's an intrusive igneous. It's non-fragmented. We have the volcanoclastic. That's going to be extrusive. It's going to be more fragmented. And then the PK unit is the pyroclastic. It's fairly similar. It was also extrusive, but more violently so, and deposited after an explosive event. And this is really the unit that is of economic interest. And so this is what we want to go ahead and try and identify with the geophysical data. And so the first question we then ask is, okay, what are the expected physical properties here? And because there's been a number of different geophysical surveys run, as we'll see, there's a number of different physical properties that are potentially diagnostic. So we can look at density, we can look at magnetic susceptibility, for example, conductivity and chargeability. And so some of the different units are fairly easy to identify. So for example, the host rock, we don't expect that to be overly conductive or chargeable, not susceptible either, and just of a moderate density. The kimberlite units, we expect those to all have a low density in comparison. We expect the HK unit to be moderate, to be relatively with high susceptibility, whereas the VK and PK is perhaps some, but not quite as substantial as the HK. Conductivity can also help us perhaps diagnose the difference between the HK and the VK PK units, which we expect to be more highly conductive because they are more fragmented, so we can get more fluid through there. Chargeability is another parameter that we'll look at, and we'll get into that. But basically, we can see, at least as far as we know here, we might have a good chance at identifying the difference between identifying the VK and PK units as compared to the rest. But there is then a question of perhaps can we use chargeability to understand the difference between these two units. So there's quite a number of geophysical surveys that have been flown in this area. So we've got the survey listed here and also their dates. So DIGCHEM was flown early, and this was, the original discovery. So frequency domain EM data, also with magnetics. There's been airborne gravity gradiometry, and then two time domain EM surveys, the AeroTEM and the VTEM. There is ground data as well. There's been nanotEM, mag, and gravity. But here what we're going to do is we're going to ask the question and focus on the airborne data and say, what can we actually do entirely from the air in terms of characterizing these deposits? And so we can look at the different airborne data. So we can see gravity gradiometry. We see some lows over where we expect these two kimberlites, so DO27 and DO18. With the mag, we see a stronger signature associated with DO27, although some hints here with DO18. You can see why the frequency domain EM really stood out, as we've got a high here and a very strong high here. And then interestingly, in the VTEM, we now have some interesting negative transients that we're going to have to handle. And so this is a motivating area and a motivating number of data sets that have led to quite a substantial amount of research by the GIF group. And, sites like this are so valuable for research, where we've got multiple different geophysical data sets, some drill hole information, and the ability, to look at it from a number of different angles. And so there's 3 different papers that have been published by the group on this site and on the work that I'm about to show you. And so what we're going to end up doing is we're going to take each of these data sets, we'll invert them all in 3D to obtain physical property models, and then we want to relate that back to the geology and see if we can build a quasi-geology model entirely from airborne data. So for this talk, we want to focus in on the electromagnetics. And so we've got then both frequency domain, we've got the DIGCHEM data, as well as the VTEM data is what we're going to focus our efforts on. And so the frequency domain we can work with. The time domain, as we've said, these negative transients are something that we're going to have to go ahead and develop a strategy for. And so some of you may know Sagi Kang, and he really undertook this work in his PhD thesis to try and work out how can we actually work with these negative transients and run 3D EM inversions that also contain induced polarization effects where we have chargeable material in the subsurface that causes a reversal of currents. So when I showed you those currents early on for our layered Earth, they're always going to be going one direction, which means we always have, positive data if we only have inductive effects. But what IP does is that we actually end up with reverse currents, and that gives those negative transients. So with a standard EM code that assumes, only conductivity, we can't handle, we can't account for the fact that there's negative transients, and so we need some development there. And so the key step that Sagi did in his work is to basically separate out the IP effects. And so to take our observed data, and what we'll do is split that into a part that we'll call the fundamental, or the EM part that is due only to conductivity or inductive effects. And the IP effect is then the difference between those two. So the IP part is basically data that we can't explain with conductivity only. And so in Sagi's work then, what he did is, this is very much like the two-step DC IP inversion, where you first invert DC data to get a conductivity model, and you use that then for the sensitivities to perform the IP inversion. Sagi's done very much taken a similar approach, but doing so now with the EM equations. And so we invert to get a conductivity model, but then we will now use his work to get the IP model, to get a pseudo chargeability. And so we'll do this. We're going to treat each time channel independently and linearize the problem. And so, as I said before, we get this sensitivity function that's going to come from the EM inversion. The IP data are then, again, just what we've observed, subtracting off the inductive component that we can model. And that gives us these data here, which we go ahead and invert. And you can start to see, okay, there's some interesting things that we're pulling out here. So the black dashed lines are where we have conductivity anomalies. And then the black solid lines, and also the color here, shows us where we have chargeable material. So you can see we've got a really strong response here up with TO18. And we've got an interesting response here where we've got, some chargeable response kind of near the edges of where we had a conductive response. So that's at the early times, but we can also look at later times. And we actually see that that's somewhat of a different response. As we now see, okay, the red lines are the ones I just showed you before. Those are those early time responses. And the green contours are where we're looking, or sorry, the black contour is where we're looking at later time response. And so we might expect there's perhaps two different chargeability responses, basically based on the nature of the pore spaces. If we relate this back to our physical properties, if we have smaller pore spaces, because we're in the VK unit, which was less of an explosive event as compared to PK, which we expect to have, larger spaces, we expect that to have a larger time constant, and perhaps the VK has a smaller time constant. So looking back, just flipping back here, if we look at these regions, we can then actually start to see, okay, perhaps we can actually use chargeability here to distinguish between these two different kimberlite types. And so what we've done to then go ahead and build up a quasi-geology model. So in the top here, you can see we've got this quasi-geology model, from geophysics. So from each of the inverted models, we've chose a threshold to define different rock units, and then basically tried to match that up with what we were expecting each of the kimberlite facies and the background to be. And so this is what we got entirely from airborne data. Not at all using drill hole information or any of the ground data. And this was the model from drilling. And so you can see some, nice features mapping up, where we've got sort of the main kimberlite unit here in yellow and here in green. And we can start to, more detailed kimberlite units based on the chargeability, which is a pretty cool outcome. All right. So we'll now go to a totally different scale. So we were, looking for groundwater, in the top, 40 to 100 meters perhaps of the Earth. Mineral exploration, we're looking in the top hundreds of meters. And now we're going to be looking in the top meters of the Earth for the UXO problem. And so I should have included a map, but there are, tons of UXO sites around the world. If we look in Canada, for example, although there's never been, much warfare here in Canada, there are a lot of training grounds. And so there's something on the order of 500 training sites from previous world wars where there are UXO that need to be cleaned and remediated. And so this is really a global scale problem. And the reason we can use EM for this is UXO are highly conductive and magnetic. And so the way we kind of typically think of this problem is we're going to use a controlled source method where we've got a transmitter. We're going to excite a response in the UXO and measure a secondary magnetic field at the receiver. Because these are actually small, compact targets, rather than solving Maxwell's equations fully in 3D, what we're going to end up doing is basically working with a dipole approximation. So it's a small, compact target, and so what we do is we parameterize that by polarizabilities. So basically the response along the different axes of the UXO. And so let's look at this example here. So a UXO is typically something that's cylindrically symmetric, and so we expect basically the two smaller sort of dipole moments or polarizabilities on the axes that are orthogonal to the UXO to be equal, whereas we have one axis that's a bit longer along the axis of the UXO. And so if we look at a plot of these different polarizabilities through time, for example, we might expect to see for UXO that these two polarizabilities, these L2 and L3 should be equal, whereas this L1 would be distinct. And if we compare that to just a piece of scrap metal, we might then expect that, okay, there's no sort of symmetry necessarily to this object. So we might have, three different principal polarizabilities that characterize that. And so our forward model, in a sense, is basically we're looking at our data here. We've got some component kind of related to the strength and the geometry of our transmitter and our receiver. And then we've got this piece here that relates the polarizabilities as well as any rotation that we have of the UXO. That's all this A matrix is here. So the L is the principal polarizabilities, and that's what's typically diagnostic when we talk about is something a UXO or not. And the standard approach would be to go out, collect some EM data, and then basically perform a parametric inversion, where what we're trying to do is invert for the position of the UXO, its rotation, as well as the polarizabilities. And then take those recovered polarizabilities, match them up with a library of known polarizabilities, and use that to perform the classification. So if we say, this looks like a small mortar, then, we can go ahead and try and match that. Whereas if we see that the three different polarizabilities are distinct and not close to anything in our library, we can classify that as scrap. The challenge with this approach is that it is a very nonlinear inversion. So you see we're inverting for angles, the position, as well as these polarizabilities. And so what's actually typically done in practice is you would run a whole bunch of different inversions, starting it from a bunch of different places, and then try and find the inversion that best fits the data and use that to perform the classification. And so we'll end up talking about a machine learning based approach for this. But before we get there, I want to show you the system that we're working with. So there's a lot of work now going into finding UXO in marine settings. And so we've been working with a group called Black Tusk Geophysics. They helped, design with GAP EOD. They helped design systems as well as software for inverting data from these systems. But here, this is the Ultra-Temma 4 system. And so there's actually 4 loops here. So these kind of yellow loop-like things are the transmitters. And then each of these little black nodes here, those are 3-component dB/dt receivers. And so there's 4 transmitters, 12 3-component receivers, and each of those receivers measures at 27 time channels. So you can see this is, a very rich multi-component EM data set that's going to be collected. And they typically actually can tow this very close to the seabed, just about 1 meter above the seabed is what they aim for. And so let's take a look. I want to show you basically what the data look like in this type of setting. So up here, we've got the system. So these 4 different colors are the 4 loops. So we have basically a loop here, we have a loop here, and a loop here. So those 3 are kind of the same size, but basically just offset from each other. And then there is a kind of a skinny, longer loop here that you're trying to excite from a different direction to kind of get multiple different excitations of this object so that we can get information about multiple polarizabilities. And so our system looks like this, and what we're going to do is it's going to be towed this way. And the transmitters basically fire in sequence. So transmitter 1 fires first, transmitter 2 next, transmitter 3, and then transmitter 4. And so that's what we're going to use with each of these different colors. So transmitter 1 is blue, transmitter 2, transmitter 3, and 4. And then we've got 12 receivers, each with 3 components that are looking that are listening to the response. And so here, for example, we're going to plot the data kind of like this, or we'll plot the geometry like this, where we've got receiver 1 is going to be these data points here. If we looked at receiver 12, that's here, and any of the receivers in between. So this kind of offset is basically because receiver 1 is here, the next one is shifted up a bit. And so of this data that you have, once you've identified, regions where there are potentially targets of interest, to take chunks of that data out and go ahead and perform an inversion and try and estimate those polarizabilities. But in looking at this problem, we've got lots of data. Those data should have relationships, and the thing that we asked ourselves is, okay, this looks like it's potentially a problem that could be very well suited for machine learning, and specifically convolutional neural networks. As the convolutions, these filters are looking basically at spatial and temporal relationships in the data. Those very much should be related to the polarizabilities. And so the question is, okay, could we actually use a neural network to go ahead and go direct from the data to a classification of an object? Another reason this is a potentially attractive problem for machine learning is because there is, available libraries of known ordnance objects with polarizabilities. And this geophysical simulations are quite fast. So it's very easy to generate a lot of synthetic training data. And there is also available field data. So if we take a look now, okay, what are we doing with a classification problem with a neural network? So often you see, this done with images, and specifically what we're going to be doing is image segmentation. And so classification, let's start off with what that is. So classification would basically take an image that has 3 different channels, so the red, the green, the blue. You're going to take that, and what you want to try and do is predict, okay, what class is this? And so the class would be, okay, this looks like a horse. If we want to do the image segmentation problem, what we want to do is actually then go ahead and say, okay, where in the image is the horse? Which pixels correspond to, this being a pixel that's in the horse versus this being a background? And so that's somewhat like a richer classification problem, because then all we're trying to do is at every single pixel, we perform a classification. And so we started out where we've got, images that are number of pixels in the X by number of pixels in the Y by the 3 channels for the red, the green, the blue. How do we relate this to our EM problem? And so this is now work that has been led by a postdoc in the research group, Jorge Lopez Alves, who has since moved on and taken up a position as an assistant professor at UNAM in Mexico City. And so what we're doing in this case is we're taking now the EM data that we have that is multi-component, right? We've got number of along line positions, we've got number of receivers, several different transmitters, different times, and then different transmitters as well, and 3 components. So you can see there's a lot of different dimensions to this data as compared to looking simply at an image. And so an important step that Jorge made is figuring out, okay, how are we going to think about how to arrange this data? And so what we ended up doing is making sure we want to take, convolutions around data where there should be relationships. And so making sure that we're kind of essentially looking at each transmitter and component of a given receiver through time similarly. And so rather than doing 2D convolutions, we'll do 3D convolutions, but it's a lot of the same machinery as what you would think about for image classification. So we'll go ahead, we'll put this through our neural network, and what we want to end up doing is at the end of the day getting out class probabilities where we say, okay, these pixels look like they're associated with an object versus the blue being background. And so an important step for this is actually then saying, okay, how do we actually generate our training data where we say this signal is actually associated with UXO versus not? When you're thinking about an image with a horse in it, it's very easy to draw that outline. But when we have EM data, we have a peak and then it decays away. And so we needed to basically go ahead and pick a strategy, based on thresholds where we would say, okay, let me take the response for multiple different transmitters. So we've got our 4 different transmitters here. And what we'll do is we'll basically just sum up the magnitude for both the X, Y, and the Z component for our different receivers. And we're going to use this to generate a mask. And so the Y direction here is the number of receivers, and then X here is our along line. So we're basically moving our transmitters along. And so we take those magnitudes and then we basically pick a threshold on that magnitude where we say, okay, this signal is due to UXO and this here is due to background. And by arranging it in this way, by kind of taking it and putting our data in this little image, we can then perform this classification and then basically send it back essentially to the footprint of the EM system. So you can sort of see these relationships here are basically the same, but slightly shifted because of where the receivers are offset from each other. But the nice thing here is once we're back to correlating that pixel point essentially with where our transmitter and receiver, or with where our receiver was, this now then has a physical location associated with that class. So we can say, these receivers here that are colored pink, when they were at this location, we think that they were seeing signal due to a UXO, whereas when the receiver was over here, we think it's seeing signal basically just due to background. So we're thinking about this kind of like in chunks. And so how do we actually apply this to a full survey or a line of data? And so what we'll do is we've got our line of data here, and we're going to do classification basically by using a sliding window. So first of all, we pick 15 along line locations, so we've colored them in red, and we're going to do our image segmentation. We'll apply that to that window first. And so we take the data that are seen by each of those receivers, and those are going to be then input into our neural network. We run that through, and it provides us back a class. And so when we're far away from these UXO, it's going to classify that just as background. And then as we go further, we basically just take that window, we slide that along, and you can see that as we get closer to the UXO, that those classes change color because we're now seeing signal that we believe is associated with a target of interest. And so we can do that, with a single object, or now we can put 3 different objects in our single acquisition line and be able to go ahead and classify that entire line. So in order to be able to now make use of this, the training data set turns out to be a really important piece. And so we pick the training set basically based on whatever objects we expect to see at a given location. And so for the Squim Bay data set that we're going to talk about, so these are field data that are collected in a marine setting in Washington State. These are the types of objects that we expect it to be able to see. And so we set up simulations where we're going to, change the orientation, we'll change the depth and the location of this UXO and run a small little survey over it. And so we generated lots and lots of examples, almost 500,000 training examples, and then set aside some for validation. Now, a really important piece is we know the polarizabilities for these objects, so all the sort of standard objects, but clutter. how are we going to handle this? And so this was a really clever piece that Jorge worked on that I think is a really cool example. So we know that we're working, for example, with this dipole model, and it takes a form that's kind of like this, where we've got a few different parameters where we're talking about, you know, the rate of decay in time for different objects. And what we can do is basically fit these different variables for the different objects that we know. And you'll end up in a cross plot kind of like this, where we've got, you know, these different parameters basically plotted out here for a given one of the polarizabilities. And what we do is basically say, okay, what I want to do is basically fill the rest of my parameter space with random assignments of these values to generate clutter objects. So what we're basically saying is, okay, we've got lots of other things that could kind of look like dipoles. And as long as in the parameter space of our model, they're far enough away, we'll generate those to kind of be able to try and classify clutter objects, things that are metallic that are going to generate some sort of response, but we don't necessarily know what it is. And so with this training set, we went ahead, we trained up our neural network, and now we want to actually look at a field data set. And so as I mentioned, we're looking at this data set in Washington State at a site called Squim Bay. These data were collected in 2022. And importantly, the first piece is that they collect data on a line where the objects are known. And so this is called a calibration line. And any system that's going to go out and run a survey is first going to go over the calibration line to make sure that, you know, the system's working properly and things like this. And so we're using this for now as our test of the neural network setup. So to cover this area, we're looking at the data here that was collected over 7 acquisition lines. And so you can see big red means we're seeing, you know, strong EM response due to some objects. So some of these, this howitzer is a fairly large object. We see there's a scuba tank, for example. There's a 60 millimeter where you can see maybe a hint of something red. And so those are the data that we want to use to go ahead and make predictions. And so in our training, we use only UXO objects. There's some of these things called ISOs. Those are basically just standard objects like a pipe that is meant to look like a UXO, which should classify as the closest UXO object. So a medium ISO should look like an 81 millimeter to our neural network. And so the first thing we do is we actually run this in 2 steps. Is we first go ahead and do basically a 2-class classification where we try and say, okay, where do we see background versus something metallic, just something that generates a response. The reason we do this is to then basically define areas where we say, okay, these areas are basically just background noise. And we found it's really important in order when we're doing the second stage where we actually want to say, okay, what is the signal from this region number 10 associated with? What kind of object is that associated with? We need to know something about the background noise to be able to do that. And so we do this first step. This allows us to estimate the background noise, and we're going to basically add that to another training set to kind of fine tune our neural network at this stage. And so we fine-tuned our neural network. It's included. It knows something about what the background noise is. And now we can go ahead and perform a classification. And so this is basically just taking that sliding window. And now we're trying to say, okay, which of these objects do we expect now to be UXO versus clutter? And so we get a map that looks something like this, where you can see the different colors corresponding to different clutter or UXO objects. So we see it looks like clutter here. This object looks, for example, like 155 millimeter. So an important question is, how did we do? And here we can look at the predicted labels versus the true labels. So the black is what the ground truth is, and the green is what the predicted label is. We can point out a couple important things. So we did identify this object here as clutter. That was actually an anchor that was used to anchor the line when they put these objects out. So they tied these objects onto a line so that they would stay in place. And that's what this anchor was. We were also able to discriminate the scuba tank that was meant to be a clutter object. Importantly, they didn't actually necessarily expect that these very small objects be picked up by the systems, but the neural network correctly classified them and identified them, which is an exciting step. And then for these objects, these ISOs, as I mentioned, which we didn't include in the training set, those ended up being classified as the closest object in the training set, which is a good sign to basically say there's a bit of sort of buffer space. If we don't have the exact object, but we know it's very close to something, it classified it correctly. So there still are some pieces, where there's room for improvement. So this east anchor, for example, was not quite classified correctly. But overall, we're pretty pleased with this as a proof of concept to be able to say, okay, can I use a neural network to perform classifications from EM data? And so the key points here is we were using an image segmentation algorithm to go ahead and perform the classification here and to identify, where in the data are we seeing targets of interest. This approach for the clutter design and capturing and including correlated noise were very important parts to have this be successful. There's still lots of work to be done. This isn't trained to handle multiple objects in the same window, which is very common, and so that's something that is necessary to go forward. And so that'll be some things that we're going to be looking at, as well as, how do we perhaps integrate this with inversion methods? The parametric inversion approaches do work very well, and so how do we perhaps, combine the best of both worlds, where inversion is working well and where machine learning is working well? And so that was a bit of a rapid fire tour through, a few different problems across a few different scales where EM can play an important role. And so I hope that's shown you, that EM can be a valuable tool. And importantly, throughout, numerical tools for simulation, inversion, and machine learning are important for a number of different angles, from an understanding and being able to visualize and characterize physical responses, but also for, an interpretation of data. And so there's a lot of research and exciting work that the group is continuing to do in these spaces. And so with that, I'll say thank you. I really appreciate you all being here and taking some time on your Friday evening to connect.